So hi everyone, I'm Fitz. So I'm a new PhD student starting this year at Monash, but I've used Phantom in my honor project last year. So I'm just gonna talk about my honor project. So my project is working on investigating tidal disruption events. Mega has talked about partial disruption on Tuesday. My focus is mainly on total disruption, which means there's no self-bonded stellar core remain after the first passage around the black hole. And although you've already heard about this, I'm gonna introduce TDE again. It happens when a star approaches a supermassive black hole. And as the distance between the star and the black hole gets sufficiently close, the black hole gravity acting on the star would exceed the star's own self-gravity. And the star is now effectively a blob of gas bonded to the black hole instead of self-bonded star. So then due to the tidal force, the gas blob will be stretched into a long stream around the black hole. And this stream will now remain in the Keplerian orbit thanks to the general relativistic effect known as the epicidal precession. Then the head of the stream will self-interact with its trailing part and rapidly dissipate the orbital energy and form an accretion disk around the black hole. So one of the main mysteries of TDEs is that due to the existence of the accretion disk, one would expect it to emit mainly in X-ray. But in reality, a large amount of TDEs are discovered in optical band instead of X-rays. And some optical TDEs do have companion emission X-rays, but others don't. And one of possibility is just to admit that we really know nothing about TDEs, and this emission comes from some unknown sources, or they may not even be a TDE at all, but some other events. Or another possible explanation is that there exists a reprocessing layer, which I'll explain next. So in 1997, Loeb and Alma has proposed there could be an optically thick gas envelope surrounding the black hole and the accretion disk, which is the reprocessing layer. When X-ray is emitted from the accretion disk, it is absorbed by the optically thick reprocessing layer, which would then re-emit in optical, and this is what we observed. But shouldn't this block all the X-ray instead? As I mentioned in the last slide, there are still TDEs observed in X-ray, so this should not be the case. A few attempts has been made to explain this. Either the reprocessing layer does not cover the accretion disk in all directions, maybe just form a torus here so X-ray can escape in this direction. But this will make the observation of X-ray viewing angle dependent thing. Or this envelope would initially cover the whole accretion disk, but would evolve, and at some point the density would drop below a threshold and allow some X-rays to escape. And this latter explanation does have some observational evidence. Like initially the TDE is only observed in optical, but later there's like X-ray brightening. But such evolution still lack theoretical study, and this is what we are trying to do. However, it is quite difficult to study TDE and its reprocessing layer. Currently observed TDEs all come from distant galaxies, and also since they happen around supermassive black holes, which resides deep in the galactic core, we cannot resolve images of TDEs or the reprocessing layers, like for the protoplanetary disks with ALMA, which you can just see the disk. And what we have in hand is only the spectra and light curves, like the ones shown here. And this really not much detail can be inferred from such light curves. So the only way to study TDE is to run hydrodynamic models with various setup and various physics, and use radiative transfer code to produce synthetic spectra and light curves to compare with observation and determine what physics is dominant in a TDE or something like that. And that's why we need Phantom and MC first. But why do we still want to study TDE if they're so hard to do? Of course, we are physicists and we like challenges, but through TDEs, we will learn not only its reprocessing layer and disk structure, but also more general physics like accretion and relativistic jets. Since TDE happen around black hole, which is a relativistic environment, we use GSPH instead of classical SPH, which is developed by David Leptai and Daniel Price. The GL method mostly works the same as the classical SPH method, except in classical SPH, we evolve the primitive variables rho v and u, which corresponds to the conservation of density, momentum, and energy. But these conservation laws do not hold in GR. Therefore, GSPH use some other conserved variables, which are derived by Monash and Price back in 2001 through Lagrangian. These conserved variables are evolved with their corresponding conservation laws, which are functions of both the primitive and conserved variables. And we will solve the primitive variables from the updated conserved ones with some root finding method for the next time step. So we used to assume an adiabatic equation of state in GRTD simulations. For ideal gas or radiation, which are two commonly used states, the gamma ad are constants 5/3 and 4/3. But for TDEs, it evolves from ideal gas dominant in the initial star to radiation dominant in the accretion disk and the reprocessing layer. So we need to account both components, and this creates a problem. Either we need to manually switch the gamma ad from 5/3 to 4/3 at some point when the density drops below a threshold and the radiation becomes dominant. But it is difficult to determine such threshold, and this will introduce some unnecessary errors. Or we could just combine the contributions from ideal gas and radiation into one equation of state, and just let the state decide the contribution of each one. But now gamma ad becomes a variable between 5/3 and 4/3 instead of a constant. So we need to know the pressure, density, and internal energy independently to fully define the state of the gas. But the existing method in GR Phantom is not useful anymore because they rely on constant gamma ad and adiabatic equation of state. We therefore introduce the thermodynamical entropy S, which can be defined in terms of density and temperature through the second tetrad equation. Note that this form is derived from second law of thermodynamics with the equation of state we chose. So it is specific to this equation of state. And to solve the primitive variables from this entropy S, we will solve the primitive density from the conserved variables as usual, but then solve the temperature from entropy S in addition. Then we can simply calculate the pressure and internal energy with the equation of state from last slide, and then the gamma ad if we need it. So this process will be repeated until it converges. With this method, we are ready to run the full TD simulations. When we run the simulations, for each setup, we will run two simulations, one with the ideal gas adiabatic equation of state and one with our combined equation of state. So in this way, we could also try to study the effect of radiation in the evolution of a TDE and its reprocessing layer. So first, I will show what a TDE TDE is expected to be. The star is disrupted into a stream of gas and itself interact to dissipate optical energy and form an accretion disk. On the left, the one on the left is the one with the ideal gas accretion of state, and on the right is the combined accretion of state. So with radiation, the gas density becomes more uniform, which is expected, as radiation with gamma at equals 4/3 is more compressible. But what I want to emphasize first is that this is not a TDE we will see. In reality, we cannot see a TDE, but only the reprocessing layer. Here are the same TDEs in the the top two are the same TDE as the one shown in the last slide, but only viewed at larger distance. And the lower two are the same TDEs viewing with electron scattering opacity. Once we add the opacity, which obviously present in reality, we can no longer see the disk inside, but only a larger processing layer. Radiation not only makes the accretion disk more smooth, but also the reprocessing layer. The one on the right here has almost uniform density in all directions, whereas the one on the left has many observable small structures. More significantly, we see big difference in temperature we obtain. With only ideal gas, the temperature of the reprocessing layer is around 10 million kelvins, whereas it is only about 10,000 kelvins when radiation is accounted. And from observation, the blackbody temperature of the TDE is also around 10,000 Kelvin. So we confirm the necessity of radiation to produce reliable simulations of TDEs. And as I've said previously, we don't have images of TDEs from observation. So these previous images are not really useful. We therefore need to produce synthetic light curves for comparison. For these ones, we only use splash to produce them, but using MC force will be our ultimate goal. Compared with observations, we see they are qualitatively agreed, and with radiation, the decay rate of luminosity is slightly higher and just more consistent with observations. But to use light curve to study TDEs, we need to first understand the effect of each parameter on the light curve. So we are currently running a grid of simulations with different penetration factors, eccentricities, black hole spins, or inclinations, which are listed here. And hopefully we will have some new results this year. In summary, to explain the optical emission from TDEs, the presence of a reprocessing layer is a promising explanation. And to study the structure of such a reprocessing layer, the only way is to compare the observation with synthetic light curves calculated from hydrodynamic simulations. However, to properly simulate the reprocessing layer, which is dominant with radiation, we need to take into account the contributions from both gas and radiation. And we implemented the thermodynamic entropy and cyclotextual equation into Phantom for this purpose. Then we start running a grid of simulations with different parameters to study the effect of each on the light curves, so we could study TDEs from their observed light curve in the future. And thanks very much. That's the end.
Thanks for the great talk, Fitz. Does anyone have any questions?
Hi, Fitz. Great talk. So I'm wondering what are the differences between using MC Force to produce light curves from your simulations versus the splash tool that you've presented? Because I know that you've had previous attempts to produce light curves with MC Force. So are there any issues that you've encountered with using it?
No, like when we're using Splash, we just give like a specific opacity instead of just calculating from physics. So with MC Force, we haven't got enough time to try with MC Force this last year, so just using Splash for convenience. And yeah. So
Okay, thanks. Yeah. Oh, sorry.
Yeah, I'll try to use MC Force to produce some proper light curve.
Okay, that sounds great. Thanks.
Are there any more questions? All right, well, if there's Daniel wants me to say, what about magnetic fields?
Magnetic field. I haven't really considered about magnetic field yet.
Yeah. Hi, Fitz. Great talk. I just want to follow up on the magnetic field comment. What about jets?
So to launch jets, we definitely need magnetic field, but just from what I've read, like usual solar type star, its magnetic field is quite weak, and we don't really know if that's strong enough to launch a jets, but it definitely do because we observe jets, but we don't really know like how you would produce a magnetic field strong enough from the weak field in a star. And for those from those simulations, from those MHD simulations that try to launch jets, they start with a disk with strong magnetic field that's much higher than in a star, so we don't really know how they connect yet.
All right, great, thanks.
Well, if there's no more questions, we'll thank Fitz once again for the great talk.